My name is Simon, and this talk is in a lot of ways going to be sort of a continuation of the talk beforehand, or kind of continuing where that talk ended. If you remember, there's a question from the audience, like, do you see the light at the end of the tunnel? And what I'm going to try to do is kind of show you a roadmap towards that tunnel with the light at the end, or maybe show you a possible future of what blockchain development could be, but also drawing heavily from the past, from the history of computing, and kind of dredge up some interesting ideas that may not have gained traction at that time, but are worth revisiting, considering the problems we're facing developing smart contracts. Now, I think we all agree that kind of writing smart contracts is kind of hard, or at least tedious, and very error-prone. There's a recent study which analyzed about 25,000 Ethereum contracts and found that 94% of them contain something that is potentially a vulnerability. Now, there are some methodological issues with this, and this number is definitely vastly overstated, but still kind of it serves as a good segue into what we're going to talk about, because it kind of shows two important things. First of all, it's the way they did this was automatically. They automatically analyze existing smart contracts and search for vulnerabilities in them. And that kind of shows us that, yes, probably we can build tools to help us and catch many of the problems. And kind of the other point is that even if 94% is a too high number, most of contracts have issues. Some of these issues just stem from a very poor engineering culture and hygiene, and some of them are actually kind of pretty gnarly bugs due to the nature of developing for blockchain. And here, we do have to acknowledge that. Developing smart contracts, or deploying something on the blockchain, is in a lot of ways a very, very alien world. Even if you're a very seasoned developer, there's still many things that can catch you off guard, or is completely non-intuitive, especially if you kind of grew up thinking about computation through a von Neumann prism. So the main problems that we have, or main challenges are, first of all, is massive concurrency. And anyone who kind of developed any sort of distributed systems knows that it's basically any distributed system in production has bugs. It's just a question of how lucky you are, whether those bugs manifest or not, and how bad it is when they do. And here we kind of have the same thing, but just the level of concurrency is on unprecedented scale compared to most of the systems in production otherwise. Second problem is that, as in most distributed systems, we have non-deterministic execution ordering. And here's even kind of worse, because you don't even know when your transaction, there's this additional element of maybe the transaction not even kind of getting included in a block and so forth. So that's another thing that kind of you have to think about, and where it's kind of different than just programming something running on your computer. First of all, it is kind of fundamentally a live system. You can't just stop the world, inspect it, or restart it and fix it, as we've kind of seen with DAO hack and the parity and so forth. Once you do something, you're kind of stuck with it, or at least you're going to have a very good contingency. And a kind of a framework that I like thinking about, just kind of development and how we should kind of organize our way of working, is this from Richard Gabriel. He says that there are basically two ways of thinking about development. There is the language paradigm and the systems paradigm. The language paradigm is kind of this very mathematical top-down approach, where essentially you start by defining your language or your axioms and then derive things within that language, within that framework. And then there's the second approach, which is the system paradigm, where the idea is that we acknowledge that what we're dealing with is a live system, and we're interacting with that live system. And here what you're doing is, basically your solution is very kind of piecemeal. You build small snippets of functionality and then kind of compose them towards solving the final problem. And at all points kind of interacting and introspecting the system. And now, oftentimes kind of the punchline that I make here, and this is a model that I deeply like, is that kind of acknowledge that there are two of them and pick the one that meshes better with the way you're thinking. There's kind of no clear winner, I think, for most kind of problems. And also just acknowledge it and also pick the appropriate tools. If you're more, for instance, on the language paradigm, you're probably going to be pretty happy programming something like Haskell. While if you're a proponent of the system paradigm, something like a Smalltalk or a Lisp is going to be a much better match. However, with blockchain, I would dare say that actually just the nature of the problem is such that even if you don't want to, you're invariably forced to at least somewhat acknowledge that we are working with this living system and interact with that and kind of play according to those rules. So what we're going to look first is just kind of what does a good development environment which fully embraces this notion of the system paradigm look like? And here we're going to go about 40 years into the past, and this is General Lisp, one of the glory days of Lisp and Lisp machines. It's like an entire operating system and development environment written in Lisp, which is by now sort of obscure programming language, but at a certain point it was one of the most promising developments in programming language design. And the thing to note here is that basically everything is inspectable. There is no clear division between your runtime, or the program that you're running on the one hand, and your IDE. It's basically just one continuous thing. So essentially what you do is you always you start with your editor, you start with your operating system, and then extend it towards solving your problem. And what this approach gives you is that all the facilities that your operating system has, all the ways to debug and trace it, just neatly flow into your problem domain as well. And it's going to turn out to be a super nice way of working with computers, but it sadly fell out of use. But there's still things that we can extract from, and something that we're going to return to at more the end of this talk. But the point for now to keep in mind is that tool selection is important. There's a great quote that, by Culkin, that we shape our tools and thereafter our tools shape us. Meaning that it's not completely arbitrary what kind of tools you use, what kind of programming languages, what kind of editor environments. All those things do have deep ramifications. And it's not just something surface level, such as productivity, but rather it shapes how we approach problems, how we think about those problems. And that can have also very measurable impacts. For instance, another study with questionable methodology, but interesting takeouts is they analyzed various GitHub products across different programming languages and look at the amount of bugs. And here we have this ranking of relative bug propensity per programming language, meaning compared to the average, how many bugs tend to projects in a certain language have. And if you look at the top three of them, you have Clojure, Haskell, and Scala. Now, Haskell and Scala are I guess, aren't a big surprise. They're languages with very good type system, which does a lot of things for you. They have a strongly academic community, which does work on things like formal verification and so forth. So no surprise there. But the first one, Clojure, is a dynamic language. It's one of the Lisp, in the Lisp lineage even. And why I think it's at the top of the list is because what it does is, first of all, it's a rather good programming language with very good affordances and a very good UX as a language. And also, a lot of the tooling that's built around it is very good and very powerful. And this does have ramifications for the type of solutions that you write and the quality of those solutions. So tooling matters even beyond just the scope of let's have some form of verification and so forth, but just how do we approach this will reflect on the types of errors you have and the amount of them. And that brings me to how we're going to do this. And the first question, I guess, this dichotomy is: is the way forward just trying to find a better programming language for the blockchain or building tools? Spoiler, I don't think it is a either-or question, but a combination of both. However, I definitely think that essentially having a new blockchain plus a new programming language is probably not the way to go. It's not necessary and couples too many different concerns. Bless you. Because keep in mind this notion of transpilation, which is the idea of compiling one programming language to another. So that means that at the end of the day, it doesn't really matter what's running underneath, that we can always write a programming language on top of what we already have. And to be honest, like for the most part, I think that Bitcoin script and the Ethereum VM are kind of good enough for most purposes. So it kind of makes more sense to think about, okay, what can we build on top of that rather than throwing away the kind of the base layer and building something new. Because I think that much more gains can be had at higher levels. But okay, so high level can we go? There's still some kind of interesting constraints when developing for the blockchain that you might normally don't have. For instance, like this notion of how limited computational cost that you can have. And that manifests in kind of interesting ways. For instance, one of them is, in the previous talk it was mentioned, issues with integer overflow. And that kind of seems in a lot of ways sort of a quaint problem to have, because like most or many modern programming languages don't have this problem, because they just kind of upgrade the number into something, so a bigger representation, something like a big integer or something behind the scenes, and you don't even have to care about it if you aren't like super performance minded. But here we have a problem, because if you do something like that, like auto-promote number, what happens is that suddenly your cost profile drastically changes, and something that was previously below the limit is now above the limit. And so kind of how do you kind of reason with things like that? Because if you just take the worst case scenario, essentially the answer is you can't do anything. So kind of, and this is kind of a very active area of exploration. For instance, Philip Walder, who is working with the Cardano project, is actively, with one of his grad students, is actively working on this problem of how to sensibly estimate costs with things like auto-promotion of numbers and so forth. So do kind of keep in mind that there are kind of limits that might be unexpected, and it's not just this, okay, we have a Turing-complete language, so you can just compile anything to anything and so forth. There are interesting other limitations. And kind of speaking of Turing completeness, like, do we actually need it? Here, I think kind of, again, yes and no. Definitely it's good to have at least one of the big blockchains that does offer Turing complete computation. But also, I think that oftentimes you simply don't need it. You even kind of can, like, to be honest, even if you look at the majority of Ethereum contracts, they don't really need it. There are already now projects which essentially compile to EVM that use some form of state-based machine approach, which again is not Turing complete, but it makes sense because it's just kind of much more manageable than what you otherwise have. So kind of this trade-off is not clear, and I think that ideally this answer is going to be kind of let's mix and match things. And then there's also the tension between privacy and determinism. If you think of like something like conjoin in Bitcoin, what happens is that suddenly kind of you lose some of the determinism of how transactions are executed, or kind of how you can trace them. And this is, again, something that kind of needs to be taken into account. But it's also a feature that oftentimes kind of you don't need. So tension here. So my proposed solution for this is to embrace this kind of different trade-offs, and that acknowledge that because we're now kind of trying to tokenize or blockchainize the entire world, we do have very, very different problems, and those problems call for very different tools. So what I think is kind of the ideal solution is to have essentially a web of different virtual machines that are tailored to kind of a specific problem, and then on top of that, an even wider variety of domain-specific languages targeting those virtual machines. Now, like, why this intermediate level of virtual machines? If you heard on the previous talk, it was mentioned that to do things like formal verification, you oftentimes want also your compiler to be verified and kind of play nice with formal verification. So it does make sense to have some intermediate target that can be pretty well understood and pretty simple. So kind of an intermediate layer like that, and which is also kind of very nicely sandboxed and so forth, makes sense. So essentially, kind of here you can think of the level of granularity that essentially every smart contract could also be considered could be running on its own kind of slightly different virtual machine, and then use the DSL that's kind of the best match for what you're trying to solve. And this kind of allows you then to do things like formal verification on a much larger scale. Why? Because we've split our problem into small chunks, and then for each of those chunks we kind of approach the problem from both sides. And this is, again, this kind of systems paradigm approach to solving problems. Nibble at the problem from different ends and then kind of slowly build up, and at some point they meet. And here kind of the idea is if we just kind of have, we know that there's this part of contract that does limited amount of things, like we have limited functionality. It also kind of, we can have a very constrained VM that it's much simpler to work with in terms of what we can prove in it and how hard those proofs are to make, or even like maybe we can do some of that automatic, can just infer some invariants. Again, like if you look at the Haskell world, they're already kind of, for instance, QuickSpec is a project where they're trying to infer invariants from test examples. So even we can go that far that it actually says, okay, I think that this and this and this are kind of properties of your system. However, formal verification is not kind of be-all and end-all. It still has problems. Like the main one is if you haven't kind of thought about it, then kind of tough luck. There's a recent example of a vulnerability in ZeroCoin, which has the distinction of kind of having its operations be mathematically proven, and at the same time turn out that there was a vulnerability in there. And the moral of the story is that the vulnerability was there because nobody thought of that this is potentially something that you should prove the property. And if you don't do that, formal verification doesn't really help. But we can kind of go further or mix formal verification with other methods to get a better coverage of the properties of our system. One of them is type holes, or kind of type hole driven development. This is kind of the most hardcore part of static programming languages and programming language theory. And the idea is that you kind of write out your types, but this can kind of become very tedious if you have to write very specific types for everything in your program. So what you then do instead of is just kind of make a sketch. You write some of them and then kind of just say, okay, then essentially leave holes in them. And then the compiler is going to go through and look at those holes, and for some, it's not even kind of a hole. It's something that you can kind of infer what the types should be here, and you can have done with it, like simple type inference. But then for some, it just says, okay, here, I can't make a decision what this is, but the options I think that are valid are this and this and this. Which type would you like to use? And then you can say, okay, this one. So like ironically, you have this like the most static way of development that if you push it to the extreme becomes actually super interactive, because now we have this interactive way where you're in a constant dialogue with your compiler, which says, okay, like then let's. How about this? How to define this pair? What this type exactly should be? And if you look at this from another perspective, it's also kind of, it's not just asking you about types, but types essentially encode some invariants. So it does help you like also to kind of uncover the areas where you might not have thought about all the kind of contingencies, and forces you to pick one, and by doing that helps you have a better and more well-behaved program. But again, even that sometimes doesn't work out, and also the barrier to entry is high. And I do think that this is important, and that some of the projects that just go, okay, let's have smart contracts written in Haskell and the problem is going to be mostly solved. Well, yes and no, because I think like one of the things that's exciting for me about something like Ethereum is also that it's essentially has, I think, like the same buzz and the same social dynamics as something like Visual Basic had, or PHP, or JavaScript, meaning that it's very, very approachable to people who just kind of want to tinker with it, who just kind of feel, oh, this is kind of a cool tech, I want to build something with it. And if we go hardcore into programming language theory, what's going to happen is that you just raise the barrier to entry so high that you lose all those people who are super enthusiastic about it, and who I think in a lot of ways are the ones responsible for something kind of achieving this mainstream adoption and becoming the de facto standard, such as JavaScript. So we should also think about other ways. And like a very good way is property-based testing. Again, something as mentioned in the talk beforehand. I'm just going to recap. The idea is that we again somehow describe what kind of data we're working with, and then just generate heaps and heaps of examples of that data and throw it against our program and see if something breaks, and if it breaks, how it breaks, and so forth. And you can also kind of usually kind of combine this with unit tests or integration tests, so we have this notion of what a correct result would be. But you can go here and like this previously again mentioned, Ikindan, whatever, is kind of a super cool example of this, written in Haskell though, but and like they do so many smart things. So kind of do check it out. Even if you kind of find the Haskell itself impenetrable, just kind of read some of their blog posts, kind of see the things that are possible if you go down this path. And like one thing that they also do, but and that demands kind of a more scrutiny, is this kind of notion that okay, instead of just blindly generate data, what about if we also have some higher level model of how users are interacting with their system and encode that model in something like a Markov chain? So basically a probabilistic model of you are in kind of, if you are in this state, then the possible next states are this one, this one, this one, and each one has a probability of going to that next state. And like what this allows you is to kind of to test for more complex interactions with your contract that can span a long amount of time. And this gives you kind of another level of assurance and understanding of what's happening. And also it's kind of just useful for things like if you want to analyze what's happening statistically, oftentimes like if you have pretty rigid dynamics, it's going to be hard to model this upfront, so you can just use property-based testing to generate millions and millions of interactions and then analyze those and just have empirical distributions rather than spending countless hours trying to figure out some math that explains it all. But then let's take it even a step further, and let's have kind of proper simulations. Something like adversarial reinforcement learning, where you have kind of different agents, each one with some criteria function to maximize its profits or something, and those go one against the other. And that kind of also kind of helps you, I guess, test your, not just the functionality per se in terms of, okay, like do I have some horrible parity-like bug, but also allows you now kind of, this allows us to test things like, is our economy kind of well behaved? Do I have some weird strategy that's going to completely decimate all other players and is going to provide a very interesting way of how people are interacting with my product? And like this kind of things are almost impossible to just kind of model up front, or even if you have kind of, because like the invariants, what they're going to do and things like formal verification is they're going to show you essentially what are the boundary conditions, what's happening at the boundary. But they don't say that much about what's the average behavior or how likely the system is to collapse in one of the steady states, while simulations do precisely that. So they kind of give you an insight of how the dynamics of the system work rather than just the steady states. And so here I think like the next big thing is going to unlock a lot of potential in the blockchain is going to be precisely using simulations a lot, especially in combination with modeling incentives and disincentives and so forth. And because this is kind of, at this point, it kind of stops being just a tool to ensure correctness, but it also can be used as a tool to help you optimize what you're doing. Because you can then do things like running A/B tests and find, okay, what happens if I do a small tweak to my contract? How does this change behavior? And if you have a system that does this alongside, you can iterate much faster and produce much better token economics. And kind of the logical next step, or kind of thinking about, okay, where all this kind of leads us, is if you look at other branches of engineering, you see that like most are using some form of computer-aided design. And here, like in a lot of ways, computer developing software is very primitive in terms of its tools. I think that even kind of we made some steps backwards, even though on the plus side, everything is essentially for free, while most people kind of pay tens of thousands or hundreds of thousands of dollars for their CAD programs. But at the same time, also our tools are very rudimentary. And I think that like just by kind of the sheer complexity of developing for the blockchain, and also I guess that there's enough money in the system that unit economics for developing something like this suddenly make much more sense. We are going to kind of see more comprehensive approaches to building development environments for the blockchain, which kind of mimic what people otherwise are doing with CAD software. And I think here the main thing is that what's going to happen is this kind of transition to building bottom-up using a library of more or less standardized and reusable components. And this is like both in terms of code or in terms of functionality, as well as in terms of economics, in terms of token dynamics that you want, in terms of incentives. And this is like precisely how most of other engineering is being done. Like you are reusing components, you kind of assemble them like very much bottom up. And this also kind of, this approach again, also ties to this notion that we should be using a vast variety of different VMs and programming language, just because then kind of each component can be done in a way that kind of maximizes the quality and the speed of iteration or whatever you want to optimize for that component, but it doesn't constrain how we're going to develop for the entire system. Again, but kind of the downside of this, or the challenge here, is that doing so kind of, in some ways, ironically increases complexity, because it's kind of, if you haven't developed all the components on your own, it makes it even harder to understand how all the parts interact. And so again, this kind of need for having good development environments, good simulations to understand what's happening, and kind of make your choices of these components more informed. Another thing that kind of this brings, and I think it's again a trend that we're going to see in coming years, is some notion of hot loading. I mean, the kind of the immutability of the blockchain is a blessing and a curse, but I do also think that in terms of building living systems, you do have to acknowledge that probably we're going to need to kind of make changes as we go along. And the current approach to just essentially hard fork and throw everything previously in some ways away is something that might work on a level of a blockchain, like on level 0, but as you kind of move on the higher levels in terms of various smart contracts, you can't really kind of make a hard fork and just forget about everything else. So what I think we're going to see is kind of more ways of doing hot loading and having a live evolving system. So we both can do things like patch and just like add new functionality as it goes along. And again, like right now, if you look at the approaches of how you can do hot loading on something like Ethereum, they look pretty scary. And it's like, well, who would want to do that? Because like that does not seem like a good thing. And it makes kind of go-to clauses look like a very solid engineering approach. But I think like as we kind of develop, like mature somewhat, we're going to see better approaches, or at least we're going to find an approach that's kind of battle tested enough that we're going to be, okay, yeah, it's hairy, but everyone's going to be using this, so it kind of becomes part of the standard. However, kind of doing this, I think, will obviously kind of will introduce a lot of additional complexity to an already complex situation. So what we need here is introspection and versioning essentially everywhere. Now, kind of on the plus side, we already have most of the components because essentially all your smart contracts have their entire execution trace already stored on the blockchain in the form of transactions. So this is already kind of here, but like what we need to do is now is pull this information into your development environment and have them kind of readily available as you are developing, or just kind of testing, or maybe you've done some simulation and then just kind of look at all the things that were happening and all the changes in both in state and changes in smart contracts. And also, like if you have well-defined approach to versioning, it also like, allows you to have interoperation between smart contracts of kind of different versions, just like when including libraries, you can have version ranges and so forth. But also kind of like, let's hope that it's going to be done better than something like the Node.js system, where everything kind of breaks every couple of months because somebody messes up something with versions. And so this is again like it's a super hard problem, but I think like it's one that we will have to solve in some way. Otherwise, just like we're going to have occur more and more technical depth as we are as we're publishing more and more smart contracts, and the entire ecosystem becomes more and more complex and intertwined. And like for instance, like already the things that people are building in other domains, like this is an example of Pyroclast. It's a tool for visualizing stream processing computation. And like if you look at what we're doing with smart contracts, a huge part of it is essentially could be modeled as stream computation or flow-based programming. And like what they do here is like interactively, although like this should be a GIF, but it's not because it's a PDF. So like what you do is like you see at every this is a kind of computational pipeline, and every step you see kind of the intermediate results and what's happening. Now kind of think beyond it. Like this is already kind of very useful if you're kind of trying to build this massive distributed system which processes a lot of things in different ways. But now kind of imagine that you could also kind of be showing here on the sidebar various things that your type system infers and various invariants and so forth, or even kind of statistics of the previous runs, and kind of give you all this information at a glance. That kind of makes not just debugging much simpler, not just understanding the system much simpler, but also I think developing it is kind of much faster because you can catch mistakes and have a much more acute understanding of what's going on. So like, I think like we need much more interactivity in what we're doing at every step and kind of seeing all the results that are kind of occurring in different steps and what those results are, and then also try and kind of have provers at that point where you can just kind of dig in. So like one thing that's kind of harmful, I think, is that the way we're now doing development, it's mostly that you either do tests up front or at the end or something, but like they tend to be kind of two distinct steps. You're writing code and you're writing tests, and those two things like don't really intermix. And that inevitably leads to having holes in your test coverage and so forth. But it's kind of, I think it's completely understandable because like UX matters, and right now kind of UX is shit for these things. So we can try to do the best that we can. But if we had better tools and the ability to kind of intermix it to much better, and also maybe have kind of help in saying, okay, this is like, you don't really have to test this because we can prove this and this and this invariant, and here we have kind of a hole and don't understand it, kind of define this more or write more tests, something like that. It will have a much more pleasant experience, and I think also kind of leading to a much better results. So to kind of put all this together and how I envision that light at the end of the tunnel, where we started at, is that development is going to be much more kind of bottom-up, building very small components, and these kind of components are going to be using cornucopia of different specialized VMs that are encapsulating state and are targeted specifically or for the class of problems that you're solving, and by that give you you and your tools a much better affordance in terms of how you can analyze them, how you can introspect them, and how you can prove things about them. We're going to have a vast library of kind of standardized reusable components, and this is going to be more kind of an engineering approach to it rather than just kind of pulling some library or something, just a kind of pretty tedious and hairy process. I think it's going to be kind of even more standardized, and also kind of just allow you to do things that essentially things like type checkers and formal verification systems are going to acknowledge the existence of these kind of components and could incorporate them into kind of building their models of the world and proving things. We're going to have a lot of DSLs everywhere. I don't think like the Solidity is going to be be-all and end-all. It's definitely Solidity or something like it is a good entry point just because of its kind of conceptual simplicity in a lot of ways, even though it's complete rubbish. But at the same time, we also I think that what we're going to see is a proliferation of different kind of languages targeted at a kind of specific problem. This is something that some language communities have already kind of nailed. If you look at the Ruby community or the Lisp community, they're like most problem solving involves writing kind of a DSL to solve that specific problem. I think that we're going to see kind of the same thing here. Just that there's going to be this intermediate step of various VMs that are going to give us kind of more desirable properties and better interoperability with our tools. Then things like interactive type-hole-driven development is like, if there is some domain where this could become mainstream, I think it's kind of developing for the blockchain. Again, the point is kind of having this very interactive development, or essentially human augmentation with various kind of small tools built together, which make you a much better and much more productive programmer. We're going to start seeing more and more smart contracts have some notion of hot loading and versioning different versions. First of all, just because it is a safety net, and also because it allows you to kind of have better and better capabilities, and does fully embrace this notion that what we have here is essentially a living organism rather than this very static system. And alongside with that, I think we should be looking at having introspection for just about anything, and looking at it, and I don't mean just kind of having some block explorer and go there, but basically having introspection available at the point where you're running code, at the point where you're debugging, at every point where you're looking and interacting with code, interacting with your system. You should also have full introspection capabilities to show you what's actually going on. And last but not least, the last kind of big component is that we're going to have simulations to help us both understand the dynamics of the system that we're building, and also kind of just be a tool that helps us optimize what we're actually doing and run experiments on a massive scale. So with all that put together and this hopefully much saner vision of how developing smart contracts can be, I leave you if you have any questions. I don't think it's kind of so much either or. If you have something like versioning, so you have different versions of a smart contract and some way, essentially protocols or contracts of how to negotiate that versioning, you can have both. And I was like, I think it's kind of, and this is like probably also my biggest gripe with people, like with, for instance, Bitcoin maximalists. They kind of take just a single view of why something is useful. Like I don't think that for all the things it makes sense to optimize for the massive, the most amount of immutability possible. Like there are some cases where yes, you should have that, and you should be running on a platform that does enable you that. But there are also a lot of kind of very, from a security perspective, trivial use cases where it still kind of makes sense to use blockchain for other reasons where you don't need that. So I do kind of think that kind of building on top, like yes, the bottom layer, this kind of settlement layer should give you strong guarantees in terms of immutability and so forth. But I think like as you build on higher levels, we're going to see kind of more negotiation about what level of immutability you actually need. I feel that this is a question of kind of what your domain is. That like if, for instance, now that it seems that we're on the verge of this like massive asset tokenization, where you will in most cases also have kind of a trusted third party in the physical world rather than just kind of completely on the blockchain and you own to blockchain, that like we're also going to see like different needs in terms of that. Like, as I said, I don't think that everywhere you need that. Like sometimes even the law that we have, like the law that we have now, kind of it does work for some use cases. And like there's also like I think there are kind of different axes of where blockchain kind of adds to what's happening already. One of them is like definitely immutability, sensor resistance, and so forth. But also like another, I think, in some cases, equally or even more important axis is just the speed of things and just kind of having this inside-out approach to kind of being data first and then everyone having this common view of data and then building around that. And like for those use cases, like if those are your primary reasons why you are moving to the blockchain, then you probably you're fine with different trade-offs in terms of what's immutable and what's not. Like still kind of maybe you want data to be immutable, but if you kind of imagine this having a huge ecosystem of different smart contracts or smart agents interacting with the same kind of amount with the same data, there you probably you want to move this concerns about immutability mostly to the data itself, and because you have the versions everywhere available, it's also much easier to just roll back, or if you bet players. Again, probably we're going to see some form of markets developing on top of that to correct for some of this, but I think that many use cases would want something like some form of upgradability or change.